I hope you'll accept or excuse this alternative format for my presentation. Since I'm integrating several points from different individuals and sources, I thought it would make for a better presentation if you saw and heard the sources themselves rather than me. This is a graphic I put together last year when I applied to the Educational Psychology graduate program here at UNM. For this presentation, I'll change the title and the bottom line question to focus on some findings from neuroscience that I believe need to be incorporated into the classroom. I'd like to begin with two premises that warrant special emphasis because I believe they are so necessary for establishing a scientific attitude about learning and education.
In his book, The Astonishing Hypothesis, Professor Crick contends that all aspects of existence can be explained by neurons.
Well, the astonishing hypothesis really is that everything about you, in the sense of your feelings, what you see, what you hear, what you do, are due to the action of nerve cells inside your brain. And it's not a new hypothesis. Essentially, Hippocrates, about 400 BC, said it was all in the brain. And it's not astonishing to most neuroscientists because that's what they generally believe. It is astonishing perhaps to many other people.
Mind is a series of functions carried out by the brain. Every single thing that you and I do, every aspect of our behavior is carried out by the brain. From the most simple reflex act, hitting a tennis ball, running, riding a bicycle, to the most creative aspects, running a Charlie Rose program. These things are all carried out by the brain.
Following are 7 points from neuroscience findings that I'll let the experts explain, then I'll briefly summarize their implications for education.
But it seems as if chimps don't have the ability to reason about unobservable things. They can reason about all the things in the world that they can touch, that they can taste, that they can see, but they don't reason about abstract things like God, ghosts, gravity, that sort of thing. They don't invent the unobservable to explain the observable.
When you learn something, you are literally changing your brain, and your brain is changing all the time.
Now here's one of the things about the brain that I've always found fascinating. It's always changing.
That's right.
My little brain will be different at the end of this conversation than it was at the beginning.
And after the whole series, you'll be a completely different person. This not only explains how we grow intellectually, but it also explains the enormous capability the brain has to recover from damage. This is also another reflection of plasticity of the brain. We also will consider that in this series.
You don't experience the world directly. The world is mediated by your nervous system.
Imagine the million fibers coming from your optic nerve. It's like a million electrical wires coming from your eyes, okay? That's what it is, like a million electrical wires. Now imagine they're fiber optic, okay? So now you're looking like one of those little fiber optic doodad balls, you know, that blink all over the place. Do you guys know what that is? Anyway, imagine you get this million fiber optic cables, and little points of light appear on those things when it sends a pulse down the cable, right? So you got a million of these guys, and at any point in time, some of them are lit up and some of them aren't. But they change over time, so it's like flowing by, and it's like a flickering noise almost, right? That is the kind of pattern we're talking about. That's a spatial temporal pattern. It's spatial because at any point in time there's a spatial pattern, and it's temporal because it changes millisecond to millisecond. That is the currency of the brain. That's it. That's what your brain works on. And believe it or not, I've said this in the beginning, I'll say it again, your perception of the world is not, it's really a fabrication of your model of the world. You don't really see light or sound. You perceive it because your model says this is how the world is, and those patterns invoke the model. It's hard to believe, but it really is true.
Yeah, so we can just try this again. So now you know what to expect. So just, fix it anywhere. It doesn't really matter where. The less you move your eyes, the better, the stronger the after effect. So this is called an after image. It's a negative after image, what you'll see. So once again, it belies, so keep on fixating, it belies a simple notion there's a one-to-one relationship between the outside world and my inner mental experiences. Because in this case, it's clearly not the case. Because here they're colors, but the colors fade. So it depends not only what's out there, it depends on the history. So clearly this naive realistic view that there's a world and here's my head and there's a simple mapping, we know that can't be true.
Your brain operates a continuously running simulation of your behavior.
How do you do that?
And we know now a lot that the brain actually has a little internal simulator. So when I send a command out and I get feedback from my arm, from vision, that's governed by physics, the physics of my body and my sensory receptors. But we now know within the brain there's a little neural simulator which says, oh, I can see the command going out. Let me try to anticipate or predict what's going to happen. And so as I'm moving around the world actually doing things, I have a little simulator in my brain simulating what's happening and trying to anticipate it. Now, why would you want one, given it's really going to happen? And there's several really good reasons to have that. One is you could, in theory, just sit here and then simulate movements to decide what the best one is. Yeah. But a really important one is one of the problems with movement is when I send a command out and get the feedback, there's about a quarter of a second delay between sending it out and getting the feedback due to delays in the system. That's a very long time if you want to play a fast tennis stroke. Right. So one of the ideas, rather than working on reality, you can work on your internal simulation, which is faster. And we can give you, John and I have a little demo we'd like to show you to prove to you this prediction. And what we've brought along is one of the heaviest books you can find in the library. This is written by Tom and Eric. It's the standard textbook in the field.
Sean has a few chapters in there as well.
So this is called the waiter task. It's very similar. It's called the waiter task. It's very similar to if a waiter brings you something on a tray, and you have a choice of whether you lift the thing off the tray or the waiter lifts it off the tray. But we'll do the waiter task. So John, I want you to support this book. And now he's supporting the book. To do that, he's having to contract his muscles. And if I wait, he might get tired if I wait too long. Normally we like to have naive subjects, but John's naive enough for our case. What I'm going to do is I'm going to remove the book and ask him to keep his hand still. And if we can just watch what happens to his hand as I remove the book. So effectively, it's impossible to keep his hand still, to anticipate the timing and to therefore relax the muscles. But if I ask John now to remove the book himself with his other hand, his brain will be predicting the consequences and he can do it without any motion at all. And this is something you can all try at home. It's impossible to learn to keep your hand still when someone else removes it because the brain is anticipating the actions of one part of its body on the other. It can do it perfectly.
That when somebody does something, your own nervous system goes off as if you're carrying out the action yourself, although your hand doesn't move. That's number one. Number two, we used to think that the sensory systems and the motor systems are completely separate. This processing of sensory information, your movement, is occurring in his motor system. So a fraction of the cells that are involved in picking up this pencil will respond when you pick up your pencil. It's in the motor system that he discovered this remarkable thing. So he made us realize that the motor systems have sensory cognitive capabilities. It's an extraordinary advance.
Okay, but so what are things that mirror neurons allow humans to do that no other species can do?
Imitation.
Imitation.
I think, there are some evidence that maybe chimps could imitate, but actually we are the only species which are good in imitating. We are the only species, and that's why we have culture. Because what you discovered, I can imitate it, Eric can imitate, and so we have culture. If we're unable to imitate, we have no culture because something discovered disappears. And monkey could not do that. So that's why we think that in monkey this mechanism is not for imitation, but for understanding. And on the top of it, it grows up our capacity.
You can imagine how much learning must go on what is really sort of an implicit mechanism. That is, it doesn't involve motor movements. It's now thought that maybe children learn aspects of language acquisition by seeing their mothers move their mouth, the mother's mouth. The child sees that and learns to do this intuitively. It's really a remarkable insight.
Your nervous system expects feedback and responds to feedback.
James Peacock has suffered excruciating pain since he lost his hand 6 years ago. This raises a perplexing clinical problem. How do you treat pain in a body part that's missing?
One answer might be that the brain is sending signals to the arm and trying to clench it, but in you and me, there's messages going back from the muscles of the hand telling you you're clenching too much or too fast, and this damps the command signals, so you can slow down. But the patient has no feedback because he doesn't have an arm. So the brain says, send even more signals, okay? And this goes on, and you get into a sort of positive feedback loop. So I said, well, if you give him some other source of feedback, such as visual feedback, maybe that'll trick the brain into thinking that the hand is clenching or unclenching, and maybe you can interrupt this loop. So I said, well, why don't we put a mirror there and have James look inside the mirror? It's as though you have visually resurrected the phantom limb. And of course, the patient knows it's an illusion, but it's very, very compelling.
Right now, as you look in there and you move your hand, your phantom does the same thing as your left hand is doing. First time I got in here and I've done this, and it was just like, it relieved the phantom pain, unclenched it. You know, it was just, oh, so intriguing, you know. Sometimes it's hard to explain how you felt, you know.
Ramachandran believes the mirror box needs to be evaluated with many patients before he can be sure that it really works. But its undeniable success in uncramping James's phantom hand suggests that even pain can be a construct of the mind.
To focus attention on any one object, your brain must suppress all other objects.
But we don't pay attention to everything we look at. How does the brain control what we focus on and what we don't? In a new study, Susana and Stephen, working with Jose Manuel Alonso, found that when our eyes track something, like Apollo's curved motion, there's more than one type of brain cell at work. One type of cell detects motion, while the other suppresses the background.
Your brain is actively suppressing the parts of the visual scene that you don't pay attention to.
And this relates to what Apollo was telling us, that when you're tracking something, that you ignore everything around it.
These two types of neurons that we are beginning to understand could explain, why magicians are so good at what they do.
Language organization, particularly grammatical structures, take years to develop and may be related to tool use.
The video's narration sometimes makes sense.
A baby penguin swings on that door. The baby
and sometimes it doesn't.
The truck goes up and down in the papers over hills.
The electrodes are recording where and when my brain reacts to these mistakes. When the mistake is simply a word that doesn't make sense,
Pinga turns up the penguin really loud.
An area in the back of my brain, mostly on the left, reacts within 0.2 of a second. But when the mistake is grammatical,
the concert are starting.
My brain pounces on the error within 1/10 of a second, and this time in a region toward the front and exclusively on the left. Following me into the video booth and equipped with a much more fetching hat is 6-year-old Danica.
Throws wood into that black stove.
When there's a mistake of meaning,
Pinga claps her ball happily.
Her brain, just like mine, reacts in 0.2 of a second. But when the video says something grammatically incorrect,
the pancake falls onto his head.
Her brain is slower to respond than mine. And the response isn't so focused over that area in the front left. In fact, Helen Neville argues, it takes perhaps 10 or 15 years for the brain to organize itself to process grammar swiftly and efficiently in just one focused, specialized region.
Looks, for example, like that's an important area for sequencing different kinds of information, and of course sequencing is an important part of language. Looks like areas just behind there are very important for tool use, in the left side as well.
Tool use.
Tool use, yeah.
Tool use over where language is taking.
Actually, it's possible that one aspect of language is closely tied to tool use, especially this kind of action planning and sequencing that we have to do in order to talk.
So what difference does this brain knowledge make in terms of educational practices? At an early age, children need to develop a strong sense of to-me-ness, recognizing that their experiences, descriptions, and meanings of the world are generated or constructed within their own nervous systems. Some abstract thoughts, or unobservable inventions that explain the observable, can be considered the epitome of humankind's achievements. But how can one discern unobservable inventions from fantasies, delusions, or frauds? Educational systems are efforts to mass-produce brain change. Student brains are not empty vessels awaiting curricular deposits. Student brains, like all brains, are active learning organs. How can schools and teachers best guide these learning organs towards socially desirable outcomes? Sensory and motor system activity can enhance learning. Exploiting mirror neurons by watching and imitating may aid and reinforce verbal skills, as well as incorporating tools, instruments, and other manipulated devices in the classroom. Given how grammatical aspects of language take years to localize, but then are more rapidly processed than matters of meaning, is there an optimum, rather than arbitrary, set of grammatical considerations that should be emphasized in education? To conclude, I'd like to share an informed opinion from the normally mute half of the Penn and Teller Magic Act.
Magic is sort of cognitive juggling. So it's this wonderful playground where you can just sort of relax and go, oh boy, it's really hard to understand the world.
We will inevitably misunderstand the world unless we understand the basics of how we, that is, our brains, interface with, react to, simulate, anticipate, predict, and construct what we can rightfully consider our world as opposed to the world. Thank you.